Okay, welcome everyone to another live session for the Massive Open Online classes, and the floor is open for your questions on any topic.
All right, so the first question from a live viewer is, does Planet X exist? And if so, how does this affect us? I don't know if they're saying Planet 10 or Planet X,
right.
Either way.
So the speculation about a 10th planet, much larger than Pluto object. Pluto is a dwarf planet, been demoted, but there's always been interest or speculation in something larger, the size of Uranus or Neptune, further out. That could have, be a legitimate planet-sized object and would influence planets inside. And that door has been left open just because the real estate in the outer solar system is large, and finding such a distant planet is difficult because it'll be faint. It'll be moving relatively slowly, so you have to take a lot of data. And I think just in the last month or so, the researchers who are doing these surveys for Planet X have pretty much discouraged the likelihood that it exists at all. And in part, they've done that by understanding the orbital properties of the outer planets, or any of the outer moving objects, including a few dwarf planets. And they've shown that those orbits are completely explained by the objects we know, the dwarf planets and the giant outer planets. In other words, typically how the last few planets in the solar system were found was by perturbations, unexplained deviations in the Newtonian orbits of those planets, which then imputed or inferred the existence of a larger object further out. And they found no such deviations or perturbations so far. So the gravitational evidence for Planet X has sort of disappeared. And the observational evidence for it by searches, it hasn't come up, and they're pretty much starting to rule it out down to a low level where it wouldn't be much of a planet at all, maybe a dwarf planet. So I think Planet X has pretty much gone away.
All right, the next question is from another live viewer, and Armando asks, does the orientation of ancient monuments such as Chichen Itza or the pyramids in Egypt change due to precession? And if so, do archaeologists take this into account?
Yes, good question. These monuments were built for a mixture of ceremonial and astronomical purposes. It's very clear that the pyramids and Stonehenge, large monuments like that, were primarily built, I would say, for ceremonial and religious purposes, and secondarily perhaps for astronomical purposes. And indeed, the alignments of those monuments is based on the times that they were built. And so, for example, if you take the Great Pyramid of Cheops in Egypt, there's a sight line from one of the tomb holes. There's a sort of a slanting passage that rises to one of the slanting faces of the pyramid, and it eventually goes down into the interior tomb. And that was presumed to be the passage by which the soul of the pharaoh would take up residence in one of the bright stars in the Egyptian sky. Now, if you precess the Egyptian sky from its current state to the state roughly 4,000 years ago when the Great Pyramid was built, that sight line, that passageway where the pharaoh's soul was supposed to emerge after death, lines up with the bright star Thuban. It was called Thuban to the Egyptians. But of course, after 4,000 years of precession, it doesn't line up with it at all. So it is, in fact, the case that on all these historical monuments, the astronomers or the archaeologists precess the sky back to the sky that would have been seen when those monuments were built, and then often the alignment drops out. So you have to do that. If you don't do that, then you can't really make that connection.
Right, the next question is from a live viewer. Ellis asks, are large sun flares dangerous in any way to Earth? Is it true or false that they can cause earthquakes on Earth?
So yes to the first part and no to the second. Solar flares or super flares, as they're called, sort of large chromospheric events. Coronal mass ejections, there's an acronym CME in the solar physics field. And these coronal mass ejections are surface activity magnetic loops that kick off enormous amounts of plasma into space. And that plasma is ejected at high speed, has very high temperature, it accelerates particles, it sends a flux of cosmic rays and high-energy particles towards the Earth. Of course, they travel at near light speed, because the radiation obviously travels at light speed, but the particles are moving almost at the speed of light, so it doesn't take much longer. Those dramatic events definitely have an effect on the Earth, but they don't cause earthquakes. Earthquakes are geophysical phenomena that are caused just by plate tectonics, by the active Earth, and they can be exacerbated by the tidal tug of the moon and the sun, in the sense that earthquakes are very slightly more probable at new and full moon, when the Earth, sun, and moon all line up to produce an extra tidal stress on the Earth, than at other lunar parts of the cycle. But really, the sun doesn't cause earthquakes in any direct way, nor does solar activity. But those high-energy particles and those cosmic rays, when they actually impinge on the Earth, the Earth's magnetosphere does protect us at some level. It's like a magnetic shield of the Earth, but they create such a torrent of radiation cascading through the ionosphere and down, sometimes preferentially down the magnetic poles, so high northern latitudes and southern latitudes get the worst hit, that impinges a huge amount of energy on the Earth, high frequency radio emission essentially. And there's evidence that these flares in the past have led to really serious problems. One in the mid-60s essentially caused the collapse of the entire North America grid. The worst effects were in Canada, but the US felt them too. So if a large super flare like this, like the kind that happened in the mid-60s, were to happen now, there's a lot more infrastructure, and as people who work on infrastructure are aware, the resilience of our grids, our electrical grids, is actually no better than it was 50 or 60 years ago. So we're probably more vulnerable now than ever before. And these would be serious effects. I mean, they would have a significant economic impact. And these super flares are very hard to predict. They're essentially unpredictable. They do happen. The sun will have a super flare every few decades, but we can't say exactly when the next one will happen.
All right, the next question is, again, from a live viewer who asks, has there been any discovery of alien satellites like the ones we send to the Moon, Mars, Pluto, or other bodies?
So that's an interesting question. The people who work on the search for extraterrestrial intelligence, SETI, they're essentially using two approaches. They're listening for intelligent signals, mostly through radio emission, because radio waves are cheap to create, low energy. They travel clean through the galaxy, are not obscured by dust, and so the speculation is that an alien intelligence would use pulse radio waves to communicate or send signals. The other method they could use is pulsed optical signals by laser. And so SETI programs underway are using both radio and optical techniques to listen for signals. But there's another issue, of course, which is that an alien civilization would send, as we are, sending probes out into the solar system, and one day, as with Breakthrough Starshot, may send probes to nearby stars. So an alien intelligence with high degree of technology would send probes to other systems, perhaps including ours. So the question, could we detect an alien artificial artifact in our solar system? And I'm not thinking now here of the monolith and Arthur C. Clarke's concept, but I'm thinking, of a small spacecraft or a space probe. Could we detect that in the solar system if it came from somewhere else and someone else? And unfortunately, the answer is no, because the real estate of the solar system is so large. The space is so large. The size of the object would be small. I mean, any civilization doing this would want to save energy, so they'd make the mass of their probe as small as possible. I mean, it could be a nanobot. It could be really small. But even if it's the size of our normal satellites, that's really tiny. And if it's not putting out a large amount of power, which it probably won't for efficiency reasons, it's essentially impossible for us to detect. So it's become a sort of trope of science fiction that alien artifacts could be monitoring us, orbiting the Earth, mixed in with our satellites perhaps, watching us, or situated around the solar system. But the practical detection of such alien artifacts is so primitive or insensitive that I think we simply wouldn't know if they existed or not.
All right, the next question from a live viewer is from Dan2, who asks, If gravity simply bends space-time rather than applying a force that pulls objects together, is there a need for a force-carrying particle like such as a graviton?
And that's a good question. So the question is asking about two issues associated with gravity. One is the idea that gravity is a geometric theory in general relativity, in Einstein's theory, where the force of gravity, if you like, is essentially replaced by the curvature of space-time, and particles or waves moving in that curved space-time essentially are just responding to the curvature of space-time. The curvature of space-time is related to the mass energy of entities in that space-time, where if it's a very dense, high-mass entity like a black hole, the curvature can be extreme. Situations like the solar system, where the density and mass of objects is modest, the curvature of space-time is modest. And then the second piece is the idea that in the standard model of particle physics, all the four fundamental forces of nature have force-carrying particles. So for the electromagnetic force, it's obviously the photon. For the weak force that binds nuclei together and also causes radioactivity, it's the W and Z bosons. These are called exchange particles. For the strong force, it's the gluons. And analogously, in gravity, there would be a particle called the graviton. In quantum theory, it's a spin-2 particle, integer spin particle, that has never been observed. So the simple answer to the question is that the hypothesis of the graviton is based on the standard model of particle physics. However, the standard model of particle physics does not incorporate gravity. The unification of the standard model has only been observed and properly understood at the level of the two weakest forces of nature. Adding in the third force, the strong force, in grand unified theories has not been proven and not been successfully done. And then melding in gravity, the weakest force, hasn't been done at all. So one of these things is going to have to give. Almost certainly, if general relativity is the correct theory of gravity, then the idea of a graviton will probably go away, and we'll have a different sort of conception rather than a force-carrying particle like the graviton. So the graviton, I would say, simplistically, is sort of like a crutch. It's a crutch using standard model of particle physics to try and understand gravity. But graviton has never been observed, and it's also not even been demonstrated that gravity propagates with the speed of light. Because if you think about it, it's extremely hard experimentally to switch a mass on and off, and therefore show that the gravity of that object propagates when the mass changes at the speed of light. That demonstration has been attempted indirectly, but has never successfully been proven.
All right, the next question from one of our live viewers is, with the launch of the James Webb Space Telescope scheduled for next year, what mysteries personally do you hope it unravels?
So James Webb is the great next project for space astronomy, the successor to the Hubble Space Telescope, 6.5 meter mirror as opposed to 2.4 meters for the Hubble. Large collecting area, an order of magnitude more collecting area. A little bit shifting to the near infrared from the visible waves that Hubble did most of its work at, and also sitting very far from the Earth in an unserviceable location as opposed to the low Earth orbit of the Hubble. Now that's an advantage because low Earth orbit is not the perfect place to put a telescope. So what do I hope that James Webb will do? Well, the project that was put on the James Webb manifest after it was designed is, of course, associated with exoplanets. Exoplanets weren't even discovered when James Webb was first conceived. With exoplanets booming now, James Webb is probably going to spend a third of its science time doing various exoplanet experiments. And the most exciting and ambitious experiment that James Webb is going to do is to try and look for biomarkers in the infrared, near infrared. Biomarkers are the atmospheric absorption features we hope caused by biology on a planet that alter the global atmosphere. On the Earth, those biomarkers would be oxygen, ozone, a little methane, and water vapor, of course. So people are going to try the analogous experiment on Earths and super-Earths using the James Webb. It's very difficult work. The simulations I've seen suggest that even for a single super-Earth at a distance of maybe 30 or 40 light years, about as close as we might find such an object, it'll take dozens of hours just to get one good little chunk of a near-infrared spectrum to see a biomarker. And it won't even be a wonderful spectrum at that point. It'll still be a little noisy. So it's going to take hundreds of hours of James Webb time to look for biomarkers on 5, 6, 7, maybe 8 exoplanets. But it's a very high priority project for the James Webb, and everyone, myself included, are very excited to see what happens.
Right, the next question is, will you please elaborate more about the WOW signal and any explanations researchers have come up with since the date of its discovery?
So the WOW signal is a famous, it's so famous people think it's apocryphal, that it didn't really happen. It's a famous early signal in the SETI, the Search for Extraterrestrial Intelligence. I'm not going to misquote it, but it's either 1977 or 1974. Sometime in the mid-70s, this signal was found. Remember that the first SETI experiments were in the late 50s by Frank Drake using the Greenback telescope in West Virginia, Project Ozma, and he only looked at 2 nearby stellar targets. Well, by the 70s, people had started to use radio telescopes to look at a larger set of targets. And one of the most powerful of these telescopes was a radio telescope at Ohio State University. I think it was called the Big Ear at the time. So that was a sort of dipole array telescope that couldn't localize very specifically a signal in the sky, but it had a lot of sensitivity for the time because it was a pretty big array. And famously, one night at that telescope, on the strip chart, because this was old-fashioned strip chart where sort of the radio signal from the telescope is turned into an electrical signal and it wiggles a pan on a strip chart to see if something is happening. There was a booming signal, a booming transient signal appeared on the strip chart, the needle just deflecting almost to the edge of the page and then coming back. And the person on duty, don't remember who the person on duty was at that time, looked up in their astronomical almanac. I mean, they were good astronomers, so they looked up to make sure there was no obvious source for this radiation, a known astronomical source. They probably checked in at the local airport and tried to make sure there were no airplanes flying around at the time. And then, having done these first set of checks, they wrote on the strip chart, "Wow," with an exclamation or a few exclamation marks after it. So this was such a strong signal. It was also very narrow. When the bandwidth of the signal is narrow, which is to say the spread of the signal in hertz, then it's a pretty good indication that it has an artificial source, because nature tends to make radio signals that are quite broad in bandwidth and in hertz. So the combination of the strength of the signal, the narrow bandwidth, and the fact that it didn't seem to align with an astronomical source on the sky, a known astronomical source, led them to write "wow" on the strip chart. And so it went into the category of, well, was it an extraterrestrial civilization sending a strong radio pulse at us that was detected by this telescope? The problem, of course, was that that signal never repeated. That telescope went back to the same part of the sky, or the next day and the next day after that, that same part of the sky repeated 4 minutes later each time due to the Earth's motion around the sun. And no WOW signal ever repeated. No pulse was seen in that direction in the sky. So with a single non-repeating signal, regardless of how strong and how interesting, you simply can't go to the bank and say you've detected intelligent aliens. So the WOW signal was sort of an anomaly, and it just goes down in the history books of SETI as something that was curious, interesting, provocative, but unconfirmed.
All right, the next question from a live viewer is there a possibility that gravitational lensing, dark matter, and dark energy could distort our observation of the history of the universe?
Definitely. So our observation of the history of the universe is based on radiation traveling through the universe. We can look out in space, and therefore we look back in time. And with telescopes like the Hubble Space Telescope, we've looked back through 98, 97% of the age of the universe, back almost to the first light, back to the first few 100 million years in a 13.8 billion year old universe. Well, that radiation seen from those early stages travels through enormous amounts of space and time, and there's a lot of matter in that space and time, and so that light or radiation, doesn't have to be visible light, it can be microwaves, radio waves, X-rays, is distorted by gravitational lensing caused by all the intervening matter. And so, yes, signals from the early universe are most definitely distorted subtly by, in particular, the dark matter that lies between us and those distant regions. And in fact, rather than viewing that as a problem, that these signals are distorted, astronomers have turned this from a bug into a feature. And so they use this distortion, this very subtle distortion, as the light is deviated by dark matter along the way, into a measurement of the dark matter. And one good example of how this works is if you take distant galaxies as faint fuzzy blobs, spirals, and elliptical galaxies that are not super sharply imaged because they're so far away, you just see pretty much a fuzzy blob. Gravitational lensing by dark matter along the way will, on average, distort the image of a distant galaxy from being perfectly circular, if it started perfectly circular, by about 0.1%, 1 part in 1,000. And so astronomers have learned how to detect this tiny 1 part in 1,000 distortion caused by dark matter along the line of sight to a distant galaxy. Now, for one distant galaxy, one super faint fuzzy image, you can't detect 1 part in 1,000. That's too hard. But in that region of sky, since the dark matter is distributed over large distances, hundreds of millions of light years, you should see systematic distortions that map from one area to another. They're consistent. And so you can average the distortions of the distant galaxies. And people have used that to measure dark matter. And that experiment has now been done with large telescopes. And it's very important because it confirms what we learned from the detailed studies of individual galaxies, which is that dark matter outweighs normal matter by about a factor of 6 to 1. So these distorting signals that apply to every galaxy in the distant universe from dark matter agree with the detailed studies of individual galaxies. So that's a very useful and important way that these distortions are turned into a measurement of dark matter. Now, dark energy also exists in the universe and is causing it to accelerate. The dark energy, we assume, has always been part of the equation. It's just become dominant as the dark matter is thinned out and the universe gets larger. Dark energy appears to have the same strength in every direction and also over cosmic time. So dark energy does not do something equivalent to dark matter. Dark matter is concentrated and clumped by gravity, and so it's inhomogeneous, and it does have an imprint on distant objects, whereas dark energy doesn't, except for making the entire universe accelerate. But the simple answer to the question is yes, these distortions, or what happens to the light of a distant galaxy, is very important in telling us what the universe is made of.
All right, the next question is from Pedro, who is on with us live, and asks, are astronomers confident about humankind colonization of other planets in the near future? What would be the implications for society when this is finally possible?
So I've looked into this. It's not my field necessarily, but I did the research to write a book called Beyond, Our Future in Space. It came out a couple of years ago. And so I got into this pretty far, and we're at a very interesting stage, because despite it being close to half a century since we went to the moon, and all we left is a few traces behind, a few landers and some footprints and so on. It seems like we've not really come very far along the road of moving to the planets and beyond. But actually, we're very close to the capability of doing this. So NASA and several private companies, in particular SpaceX, run by Elon Musk, and Blue Origin's run by Jeff Bezos, the Amazon founder, are developing the heavy rocket capability that will be sufficient to get to the moon and would be sufficient to start a lunar base. So whether the government does it, whether it's done by governments, and the Chinese are interested too, so whether the US or the Chinese do it as a government project, or a couple of these private entities do it in a very competitive way, they're competing. Musk and Bezos are competing with each other step by step in the private space sector. I think it's fairly likely that within 20 years there will be a rudimentary lunar base. By that I mean it will not be fully self-sufficient. It'll be a moon base with maybe 4, 8, 10, 12 people at the most, and it will exist and persist just because of resupply from planet Earth, which is a pretty expensive model. So that, I think, will happen in roughly 15 years, maybe 20 years. The next step beyond that would be full self-sufficiency, and that requires a lot more. That requires a lot of infrastructure to generate water from the lunar soil, to decompose lunar soil to get the oxygen out, because you need the oxygen to breathe. You need to combine it with hydrogen as rocket fuel to move around and get more resources. That can be equally well done on Mars and on the Moon. So on a time scale of maybe 30 or 40 years, you have the possibility of self-sustaining bases of operation on the Moon and Mars, by which I mean people who live and die on the planet or the Moon and don't come home and don't need to be resupplied from the Earth. So I think we're headed in that direction. There's enough interest in it, whether governments do it again or the private sector does it, whether some of it serves the goal of tourism or for pure exploration reasons. I think it's going to happen.
All right, the next question is from a live viewer again, who asks, if the universe is expanding, does that mean that more universe is being created, or that the current universe is stretching? And when we say universe, what do we mean by the universe?
Right, so we'll start with the back end of the question, because the definition of universe is becoming a little subtle in cosmology. I mean, the simplest definition of universe is all that there is, everything, matter and radiation, everything in creation, everything that we can possibly see with our telescopes. So astronomers right away have to make a distinction between the physical universe, all that there is, and the observable universe, all that we can see. Because of the expanding universe and the finite age of the universe, we already know that the physical universe, all that there is larger than the observable universe. In other words, we can't see everything there is. Our limit, our view, is defined by the distance we can see in the time that light has traveled in 13.8 billion years, the age of the universe. It doesn't mean that's the edge of physical space. So there's almost certainly more stuff out there. How much more? That's a matter of models and speculation. Could be a lot more. So that's one distinction as far as the universe goes. So there can be stuff beyond that we haven't seen. And with the acceleration of the universe that we currently witness, that stuff, that space, stars, galaxies, whatever it contains, is forever unobservable, because it's just being carried away from us faster and faster, faster than light speed, in fact. So that's one issue. But to the basic part of the question, the first part of the question, we don't have to hypothesize something beyond the physical or the observable universe. We can just conceive of this one expanding space-time. We have no evidence for anything beyond that concept. And so that, in a sense, is our universe. And we don't need to conceive of anything else. And the universe we live in is expanding space-time. So in answer to the question, it's the concept that the space-time itself is unfolding or expanding. The distance between any 2 points getting larger as time goes by. And it is literally space-time expanding. Now, space-time is invisible, and if we didn't have galaxies as markers of space-time, we wouldn't even know that space was expanding, let alone accelerating. So it needs observational cosmology, it needs astronomy to really diagnose the expansion of space-time.
Right, the next question from a live viewer is, what is the latest on gravitational waves? Are there any recent updates?
So the most recent public result involved the announcement of a third gravity wave detection, and similar to the first two, a sort of large-ish black holes, which is to say black holes left behind when pretty massive stars die, stars with dozens of times the mass of the sun. So that third event was very strongly detected, and it joins the previous two. And then there's a fourth marginal event that they've not declared a true detection because it fell below the significance threshold. Almost certainly, people think that buried in the data are more gravity wave signals. So now that we've gone beyond a couple of gravity wave events, this field has become a real science. And so in the next few years, we can anticipate that gravity wave science will become a mature field, which is to say we hope we'll end up with a dozen, maybe 24 events to study to learn more about the systematics of the black holes that form these binary pairs and then coalesce to produce gravity waves. Maybe we'll learn about how stars die and what the parent population of stars is. And possibly we'll find a surprise. We may find the first gravity wave event was surprising. The the black holes were several dozen solar masses each, which is unprecedented and really unexpected. If we start to find in the first wave of gravity wave events that these massive stars, these massive black holes, are quite common, then we're sort of going to have to rethink our idea of how stars form, especially massive stars, because there simply shouldn't be that many massive stars forming. So gravity wave science is about to get very interesting because it's going to go into sort of production mode, as I would put it.
Right, the next question from a live viewer is, do all supernovas result in black holes, and how are supermassive black holes at the center of galaxies formed?
So no, not all supernovae result in black holes. In principle, when a star dies as a supernova, it is a massive star, and the supernova, the brightening event that we see as a supernova and the ejection of gas and high-energy particles is caused by the core collapse when the gravitational support is lost as the fusion is exhausted because there's no more nuclear fuel. After iron, there is no more nuclear fuel. That's the most stable element. And so the core collapses, and in the rebound of the collapsing, gravitation and collapsing core, the fierce acceleration and the blast wave heats gas to temperatures of several billion Kelvin, and that glowing gas, and there's heavy elements created in that blast wave, and the glowing gas centuries or millennia later we see as a supernova remnant. So that's a supernova. Now as for what's left, that's the outward going part, and it's anywhere between a quarter and half or maybe even more of the gas typically in a supernova. Now in the model of supernova formation, that collapsing core can actually do three different things. Depending on the mass of the core as it collapses, it could be a neutron star, which is something that is between 1.5 and about 3 times the mass of the sun, or it could be a black hole if the collapsed core, the supercompressed core, is more than 3 or 3.5 times the mass of the sun. However, it is also possible, and simulations confirm this with supercomputers, that in the core collapse and subsequent explosion, the entire object detonates. It just obliterates itself, and there's nothing left. So a third possible result of a supernova is nothing is left behind, and all we see is the blast wave and the exploding hot gas. And then the second part of the question was about supermassive black holes, and that's really a different phenomena entirely. Massive or supermassive black holes are objects at the centers of galaxies, including our own. Our own has a black hole of mass 4 million times the mass of the sun. And these are the central pileups of stars that the center of every galaxy is very dense compared to the periphery. And in these central regions, various dynamical processes can naturally lead stars to pile up into a dense star cluster, and eventually, at sufficient density, that meets the formal definition of a black hole. But in this case, it's a very massive black hole. It'll be hundreds of thousands or millions of times the mass of the sun in a modest-sized galaxy. And in a big galaxy, and especially after some billions of years of accretion, the black hole can range anything up to a few to 10 billion times the mass of the sun. So the supermassive black holes are a different phenomena entirely. They're based on extremely dense regions at the center of all galaxies, and their natural evolution towards a superdense state, which eventually meets the definition of a black hole.
Right, our next live question is, how will the device known as starshade work, and how will it help future telescopes in space?
So one of the challenges, especially in the exoplanet field, is to suitably remove scattered light and suppress a very bright point source so as to see faint things around it. It's not just for exoplanets. There are all sorts of scientific reasons why you might want to do that. You could, for instance, have an active galaxy that is a quasar, something where there's a supermassive black hole that's extremely bright, and you might want to see the surrounding galaxy. And so you might want to blot out that central quasar. If it's an exoplanet, it's a central star you want to blot out so as to be able to make an image of the exoplanet. So there are various optical methods to do this. And one component of these methods of achieving high contrast imaging in the presence of a bright source that you don't maybe care about so much and something very much fainter that you do care about is a starshade. The starshade is a mechanism just by occultation to remove the bright star and also reduce scattered light. We don't tend to think about scattered light as being an important issue in optical telescopes, and when you're not pushing them to the limit, it really isn't. But scattered light exists on all telescopes because if you think about it, the light that comes in and is focused by a large telescope is not all of the light that's coming into the dome. The dome is getting starlight or Milky Way light or whatever coming in at different angles, and that light is also hitting the telescope structure itself because the primary mirror is sitting inside a structure and there's an extended structure that holds the secondary mirror above it. So light, even faint light, bouncing off that structure can work its way into the detector, and that's confusing. So you need to reduce all forms of scattered light, and star shades are one way of doing that. So for these super high resolution and high contrast imaging telescopes that we're planning for the space environment, a star shade is essentially an ingredient that they all have just to give the highest contrast imaging. By that, what do I mean? High contrast imaging on ground-based astronomy is typically anything where the weak thing you're trying to detect is maybe 100 million times fainter than the bright thing that you don't want to detect or you want to suppress. In space, and with star shades and apodizing optics, you can generate contrast levels that are billion to 1 or even 10 billion to 1. So you can do super high contrast imaging with these methods.
Right, the next question is just a basic one about what are exoplanets. You've mentioned them a couple of times, and somebody would like to know what an exoplanet is.
Yeah, so good basic question because they're in the news a lot, and the terminology varies. So over the history of this field, which is a few decades now, some people have used extrasolar planet and some people have used exoplanet. So to a professional astronomer, those are interchangeable. But I think in the media now, and even in the professional circles, exoplanet has sort of taken over. It's a more compact way of talking about them. So exo means beyond. It's a Greek word, the root of the Greek word for beyond. And so exoplanet means planet beyond, meaning beyond our solar system. That's the way to remember it if you want. And so an exoplanet is a planet orbiting another star, any star other than the sun. And as we speak, we've measured, and mostly through the Kepler mission, over 4,000 exoplanets, or planets around stars other than the sun. A number of those systems have multiple planets. So there are less stars involved than there are exoplanets because many of the stars have multiple exoplanets. But that's part of the game too, is to measure how many planets there are around a typical star other than the sun. And this game is also extended to not just look at sun-like stars, but to look for planets or exoplanets around stars that are not like the sun at all, especially red dwarfs, since they outnumber sun-like stars by 100 to 1.
All right, the next question is from Dira, who asks, Professor, is the Mars mission a wise decision for humankind? Should we just focus on making our planet Earth a better place?
Well, yes, I think we should focus on improving the Earth and saving the Earth from our own bad behavior. And I think we need to do that. The question is there any utility to be gained by going to Mars at all? So there's sort of two ways I would put this. I mean, there's an effort on Mars to look for life under the surface, or evidence of ancient life on Mars. We know that the surface is pretty much sterilized, and so we're not going to find living creatures or microbes, and we may not even find fossilized life on the surface. But if you go under the surface, it's possible there are microbes there right now and liquid water. So I think that experiment, the experiment of finding out whether perhaps the nearest planet we can easily get to has life along with the Earth, would be an incredible discovery. And I think that makes it worth it. It's a little less easier to justify. It's a little less easy to justify habitation on Mars or colonies on Mars or a Mars base, because that's really very expensive, and it doesn't necessarily serve any larger purpose for humanity. We're never going to have the money or the resources for any significant number of humans to leave the Earth if the Earth becomes uninhabitable, even if we were able to make Mars habitable, which is also a crazy proposition in terms of time and money. So in the sense of Mars colony, I would agree with you. We're better off putting our resources in keeping the Earth habitable and a comfortable and healthy place to live. But I think many astronomers and even many members of the public would really want to know the answer to the question, does Mars harbor life?
All right, next question is from Richard, who's on with us live, who asks, what are the chances that Betelgeuse, when it goes supernova, could irradiate Earth? And asks something about it could shift its gamma ray burst to be closer to the Earth, I guess, because it's inclined.
Right. So
the poles are not pointed directly at us.
So there's obviously concern if any star that's near us, and we're talking about a gamma ray burst, the amount of energy focused in those two beams is so amazingly large that if they were within a few thousand light years of the Earth, including the distance to Betelgeuse, one of the stars in the constellation Orion, then we would be in trouble. Betelgeuse is indeed a star that will die violently, and we know that. However, our measurement of its rotation axis is very imperfect. It's a difficult star to study in detail because it is quite far away. And so I would say we simply don't know with any confidence what the orientation angle of that star is, and therefore we can't say if it goes violently as a gamma ray burst, what direction the burst will be pointed. So there's no reason to believe that it's going to be pointed at the Earth, but it might be. The second question, of course, is when is this likely to happen? And there also, we simply don't have enough information. We know how to model stars late in their life, and we know roughly what evolutionary stage Betelgeuse is at, and it is indeed an advanced massive star that will die violently. But the question of to when it will die, we simply don't have good enough stellar models, nor do we have good enough observations of the exact evolutionary state of Betelgeuse to put a number on it. That number could be millions of years, tens of millions of years, I think even hundreds of millions of years. It doesn't have to be right now or soon. And that's just a frustration of astronomy, that the precision with which we can predict outcomes for individual stars is still quite low.
Right. The next question is, how did the Cassini satellite manage to function over the years while having zero fuel?
So Cassini is, the energy source for Cassini is plutonium. Now, Cassini was sort of the last of the controversial missions. So Congress was generally in favor of allowing NASA to use radioactive energy sources because as you go into the outer solar system, solar radiation weakens to the point where solar panels are just not very efficient. And so outer solar system missions for decades have used plutonium-238 as their power source. They have a little radioisotope package, and it's essentially the sort of radioactive decay turned into heat and therefore into electrical energy through thermocouples that powers these missions. And that's a pretty efficient energy source, radioactive decay, radioactive heating. So these packages, these radioactively powered packages for outer solar system missions have been the standard way of doing that. But NASA started to take flack from Congress about the possible danger to the Earth, that when these missions were just launched and near the Earth, or if they swooped by the Earth to get a gravitational assist subsequently or something like that, there was some significant chance that the radioactive material would end up falling into the Earth's atmosphere and onto the Earth. Now, it's a pretty small amount of radioactive material in absolute sense, but of course, it's extremely dangerous. So NASA had to take this seriously. And NASA was prohibited for quite a while from planning or conceiving of a mission that used a radioactive power source. And that's very limiting. I'm not sure of the actual current status, but I think Congress has sort of backed off on that prohibition, so NASA can now consider it again. But essentially, for all outer solar system missions like Cassini, you need radioactive power source, and that's indeed what Cassini is used. So in that sense, it's not running out of fuel. It also does need slight amounts of fuel for small-scale corrections, and indeed it has run out of that small amount of fuel. And the timing is fortuitous because Cassini was already past the end of its mission. It's been multiply extended. And so when Cassini dies plunging into the planet that it's been studying for so long, it'll still live longer than it was ever designed to live.
All right, the next question is, what causes planets in our solar system and celestial objects in our galaxy to orbit in a plane or disk?
So the disk orbital properties of solar systems or galaxies are caused by the same thing. They're caused by angular momentum. So we have to imagine a very large and nearly spherical cloud of gas and dust. It could be solar system size in the case of our solar system, or galaxy size in the case of our galaxy. And of course, in practice, that gas cloud the size of our galaxy is going to subcollapse into stars as well as a single galaxy. If that cloud was perfectly spherical and had no rotation, then it would collapse perfectly spherically into a spherical symmetric object. But on average, gas in the universe has some turbulent motion. It has some chaotic or random component to its motion. So it's unlikely to be perfectly spherical or perfectly uniform in its rotation. And that variation gets amplified in gravitational collapse. So something that's large and low density and rotating very slightly will turn into something that's smaller and higher density and rotating more rapidly. And the gravitational collapse will occur preferentially along the polar axis, along the axis of the rotation. And so that's how you end up with a large, diffuse, slightly rotating gas cloud turning into a small, dense, rapidly rotating disk of gas and dust. That happened in the solar system, and then subsequent evolution through gravity led to the formation of the planets. So we think we know the processes that lead to nearly spherical systems with slight rotation turning into disks after they collapse. It's pretty standard physics, and we think we see it operating on very different scales in the universe.
Next question from a live viewer is, why is the North Pole of the planet Saturn a hexagonal shape? How does it rotate, and how is it kept that way?
As I understand it, the hexagonal shape that's been seen in some of the images is somewhat of an artifact. The only natural place, the only place in nature where I've seen hexagons emerge from stochastic or random processes is in the cooling of basaltic rock, places like Maid's Causeway in Northern Ireland, where you can see these amazing stone columns that have hexagonal shapes, because as the rock cools, the stresses in the rock and the crystalline form of the rock will lead it to form hexagon structures. Nothing like that is happening in the case of Saturn. So those hexagons that you see are largely an artifact. There is some slight symmetry imposed by the nature of the rotation, but it doesn't lead to a strictly hexagonal pattern.
All right, the next question is from a live viewer. Alexander asks, so there's a news story about a crowd-funded pyramidal Russian satellite that is going to be launched that will reflect sunlight down onto Earth. Is that really a problem for astronomers?
So this is one I'm going to punt because I haven't read this story, so I'm not sure what it's about. Just to comment on two aspects, I mean, the crowdfunding or crowdsourcing of funding of space missions is a new-ish phenomenon, but it's really quite promising, because with nanosats and small-scale miniaturized electronics, the bar is lowered for near-Earth observation to prices that are tens of thousands of dollars. So we're going to see more and more of this sort of crowdfunding of space missions by entities that are not large corporations or government agencies. So that's exciting. But of course, all sorts of missions are going to get approved, and we may not be interested in all of them. It sounds like this one is involved in funneling light onto the Earth, and the concern of astronomers, of course, with all such missions is that they're going to create light pollution or contaminating radiation that will interfere with dark sky astronomy. So when the private sector ramps up and these crowdsourced satellite missions are available or possible, then there are going to be some that'll be doing interesting things and interesting research, and there'll be some that'll be just purely commercial and they'll be designed to make money. And some of these may not be good for astronomy. The one that I was being asked about, I simply don't know. I'll have to go off and look, so I don't know if that's bad for astronomy or not. But astronomers are pretty wary of this wild frontier of commercial near space satellites, because some may be bad for optical astronomy.
Right, the next question is, planets Jupiter and Saturn have many moons. What is the purpose of so many moons for these planets?
The moons don't have a particular purpose. They're a natural byproduct of the formation of the planet. So just as the solar system was a situation where 99.9 roughly % of the mass goes into the central star, and the remaining gas and dust forms a set of 8 planets, 4 rocky core planets in the inner solar system, and then 4 rocky cores surrounded by gas mantles in the outer solar system. So a miniaturized version of this happens when a giant planet forms, where most of the mass goes into the giant planet, and in the surrounding disk, gravity causes moons to form out of that surrounding disk of gas and dust. Now, in the case of the giant planets, all the moons, even the largest moons of the giant planets, are very small fractions of the mass of the underlying planet. But this process of gravitational aggregation leads to dozens of moons. And so in each of the cases of Jupiter and Saturn, there are over 50 moons. And the limit is a little arbitrary, because there are clearly more and more moons the lower you go, and the smallest moons that have been detected are just a few miles across. And it's unlikely, it's likely that there are more moons that are just too small to detect. So literally there are dozens and dozens of moons around each of the giant planets, including Uranus and Neptune. They're just far enough away that we don't have a good catalog.
Right, the next question is, if the universe is expanding, does that mean that there is a center of the universe?
No, the expansion of the universe does seem to imply at first glance that we're in a special position if everything's moving away from us. But because we are embedded in 3-dimensional space, plus 1 dimension of time, so 4-dimensional space-time, the expansion is occurring in every one of those axes, x, y, and z, simultaneously. And the expansion of space is carrying all galaxies away from all other galaxies. So if we could do the hypothetical experiment, the Gedanken experiment in the German, as Einstein would say, of situating ourselves on another galaxy, not our own, and not M31, that's a nearby neighbor that's held to us by gravity, so let's go further away, maybe past the Virgo cluster to some distant spiral or elliptical galaxy, and we did our same observations of galaxy distances and velocities, we'd plot a diagram as Hubble did and see exactly the same thing, exactly the same slope, implying exactly the same local expansion rate. So in the hypothetical where other observers situated on other galaxies try to measure the expanding universe, they measure the same thing. And therefore, either they are concluding that they're the center of the universe, so we are, they are, everyone will infer that. Either they're all right or none are right, and that no one's the center of the universe. And the answer, logically, is that nobody is right. Every galaxy is moving away from every other galaxy. There's no privileged position in this expansion, and therefore we are not the center of the expanding universe.
Right, so the next question is, the person asks, if there were no neutral atoms after the Big Bang and light is created by electrons moving from high energy levels to low energy levels, was the universe opaque? Or more generally, what did the universe look like right after the Big Bang?
So right after the Big Bang, yes, the universe was opaque because the universe was a plasma. So plasma, in physics terms, is a gas where the electrons are not attached to their nuclei. And then most of the universe, of course, early on, before stars form, is hydrogen and helium, the 2 simplest atoms. So we have to imagine the universe for the first tens of thousands of years, even a few 100,000 years after the Big Bang, as being a very hot particle soup, a gas, a plasma of electrons and protons for the most part. No stable atoms. And in that case, what happens to radiation in this hot, dense universe with a lot of free electrons is that radiation interacts strongly with the electrons and it's scattered. And so radiation is bouncing around. This radiation at this time is very high energy because the universe was hot, so it could be maybe X-rays or ultraviolet rays. This radiation is bouncing around, cannot travel freely, and so the universe is opaque. It's like being in a fog. The landmark event that occurs is about 380,000 years after the Big Bang, when the universe was about 1,000 times smaller and 1,000 times hotter than it is now. So it's a temperature of about 3,000 Kelvin. That's a temperature below which electrons can stick to protons and form stable atoms. So neutral atoms, essentially. And as soon as the electrons all pair with the protons in hydrogen and 2 electrons pairing with larger nucleus for helium, then the electrons are no longer scattering radiation because there are a lot of small stable atoms that are electrically neutral, and that radiation can travel freely. So at that point, the universe becomes transparent. So that's the fundamental transition in the history of the universe. When the universe passes down through about 3,000 degrees Kelvin, when it's about 1,000 times smaller than it is now, and the stable atoms all form in a relatively short period of time, neutral atoms, and radiation travels freely. And when we look back towards that time, that's what we see as the microwave background radiation.
All right, so we're going to do 2 more questions. The next question is, the interpretation of observations is that space is expanding. An equally valid interpretation would be that space remains the same, but matter is shrinking. So why is that interpretation ignored?
And actually, matter is shrinking. So the question makes sense because actually both things are going on in a sense together. So just take the example of how galaxies form. Within expanding space-time, matter is clumping due to the force of gravity. And the collapse of a large gas cloud in a deep potential well of mostly dark matter does constitute the shrinking of matter, of the large aggregation of matter. So as galaxies form, they shrink by perhaps an order of magnitude, but it's within a context where overall space-time is expanding. So in practice, in the formation and evolution of galaxies, the matter concentration, the dark matter too, and certainly the visible matter is shrinking even as space-time expands. But we can't explain away the entire expansion of space-time in terms of the shrinkage of matter, because these are 2 separate effects. We can see the gravity of the matter in space-time of whatever size it is at a given time as being explained by the gravity of that matter acting on itself and neighboring regions. And then the larger landscape of the universe, the space-time itself, is expanding at a rate we can measure by marking the galaxies, using the galaxies as markers of space-time. But the question is good because both things are actually happening at some level. There is shrinkage of the physical objects of the universe as they contract by gravity, even as space-time around is expanding.
All right, the final question that we're going to answer today is from a live viewer. Alexander from Brazil asks, are radio waves generated only artificially, or is there a natural source?
There are definitely a lot of natural sources of radio waves. So radio astronomy came of age in the 1930s. Radio technology, obviously radio waves were harnessed on Earth and understood by Guglielmo Marconi, of course, famously in the early part of the 20th century, 19-teens and 1920s. So that was the harnessing of radio waves, the creation of radio waves and their use for communication. But as soon as we learned how to detect radio waves for terrestrial purposes, or with a telescope we could point out into the universe, we found that there were radio waves coming from the universe. And the first and largest signal of radio waves in the cosmos was seen from the Milky Way galaxy itself. So as people built their early radio telescopes, and in this I'm thinking of Grote Reber, who for I think 9 years was the only radio astronomer in the world. He built his own radio telescope as an amateur electrical engineer and radio astronomer. And he preceded Carl Jansky, who sort of took radio astronomy into the mainstream. So these early people using radio telescopes to look out into space saw enormous radio signals coming from the center of our galaxy, or the disk of our galaxy, the sort of plane of the Milky Way. And the physics of that is that the galaxy itself is filled with radiation that comes from stars when they're supernovae, for example, or high energy radiation from stars, which accelerates electrons in magnetic fields and leads to synchrotron radiation. So when an electron accelerates in a magnetic field, it releases energy that typically comes out of radio waves. It has some polarization, and that is called synchrotron radiation. And these radio astronomers were measuring this natural phenomenon of the Milky Way galaxy, of high energy particles in the plane of the galaxy, and also particles surrounding dying stars or supernovae. So right from the 1930s, cosmic sources of radio emission were found. And without going too much into the history, move forward into the 1950s, when radio telescopes got able to distinguish sharp or small regions of sky by interferometry, then we started to realize there were discrete sources of radio emission, not just the big extended radio emission from the center of our galaxy and the whole plane of the Milky Way, but very particular sources of radio emission. And these radio galaxies, and eventually quasars, were places where radio waves were being produced in the environment of supermassive black holes. So we've learned over a long period of time, going back to the 1920s, that the universe does make radio waves by natural processes of various kinds. And thank you for a very interesting and wide-ranging set of questions, and we'll be back with you in a couple of weeks.